Welcome back to the Gas Compression Podcast. I'm joined for the fourth time in this series for with Jim Dettore of FAS Training Services. That stands for Failure Analysis Services, and we're talking about fretting today. We've talked about abrasive, adhesive, and corrosive wear, and now we're talking about fretting. So Jim goes all over the country, all during the year, and puts on classes and does very extensive training service. Does training classes for folks in our industry. And also recently, he's taken over the What Went Wrong section in the Gas Compression magazine. Norm Shade started writing that, I don't know how long ago, but Jim was a perfect person to come in behind him and do that. So if you're not subscribing to the Gas Compression magazine, you need to, because Brent Haight and his team just do a fantastic job. He even has a section where you can listen to some of the articles that have been written. So Jim is he's a teacher, he's an author, and he just does a great service to our industry. So welcome back, Jim.
Hey, Michael. Again, I put just a brief presentation of some slides that represent some of the things that we see. Guys can use them for reference later on. So let me just go ahead and share this right quick. All right. So when we start talking about getting into the fretting realm, there was a bit of confusion with me. The way I was taught, it was all called fretting. And a few years ago, I did a good bit of study on the topic from multiple resources, and we break it into two types of fretting now. We call it general fretting, and then what's known as fretting corrosion. And the two anomalies, when they happen, they tell us some factual data about what's going on with that particular component part or those fasteners. But not only that, they also can tell us that maybe we've had a joint that was bolted together that's being overloaded and forced to move as well, right? It also tells us something possibly about fastener torque and things like that. But when we get into the different types of fretting, the general fretting and the fretting corrosion, the parts exhibit different road signs or different factual data, and I'll do my best to try to explain those to you as we go through this. So we're talking about surfaces that are clamped together tightly with fasteners. And sometimes the fasteners come loose. When the fasteners come loose, if all the fasteners come loose and the bolted joint separates, what we tend to see is what's known as general fretting, meaning that the surfaces that should be bolted together are moving, and they're sitting there and they're vibrating and they're oscillating against one another. And what this does is it highly polishes the surfaces. Almost, when I say highly polished, like they almost look like they're chrome plated if it runs like that for long enough. The surfaces of the fasteners will exhibit the same characteristics as well. So I've got a slide here with a couple of fasteners. This is known as general fretting when parts are loose. So we can tell that the lower bolt, the bolt on the bottom there, has been running loose for an extended period of time. And the way we can tell that is the threads on the bolt. If we start up in this area here, and we see the threads, that there really isn't much peak on the threads. Can you see that?
Mm-hmm.
This is a little bit of impact damage after the fact here. Bolt probably got dropped or something, but they're very, very flat. But then we see peaks on these last two. Well, those last two are probably sticking through the nut and they're not contacting anything. But these guys here, since this bolt's running loose, those threads are that thread peak is just sitting in that thread and they're moving around and they're wearing themselves flat. It also tends to polish this area of the shoulder and the underhead clamping surface. So when we have a fastener and we pull it out, and maybe somebody had tightened it up previously, and we pull it out and we look at it and we see these road signs, we know that that thing's been running loose and somebody has retorqued it or retightened it. Where in this case here, it should have been replaced rather than retightened. If we take a look at the top bolt, we see that the thread peaks are intact in this area here, and we don't have the polishing like we do on the lower bolt. This bolt is also broken on the end here. And then we've got a little bit of plastic deformation. We can see how that top thread is pulled and that bolt's kind of bent. So these bolts, both of these bolts here, hold a connecting rod cap onto a connecting rod in a heavy duty natural gas engine. So what's happened is this bolt came loose for whatever reason, whether it was fastener torque or debris or improper installation, something like that. So when this one came loose and it came out, the rod hinged open and this one was torqued tight and it broke. And then it sat there and rattled around for a little while in the oil pan. But when we see the polishing on the fasteners or on the part surfaces, those are a pretty clear indication. Hey, I've been running loose and I've been vibrating or oscillating against the part that I'm supposed to be clamped tightly against, and we polish the surfaces. So it gives us an indication that maybe we need to check torque. Maybe we reused a fastener one too many times and we've over yielded that fastener and it couldn't maintain its torque. Maybe there was debris between the clamp surfaces, and once we break that debris down, we lose the torque on the bolt as well. So gives us some good ideas about which direction to go and where to look and what questions to ask. So any questions on this one, Michael?
Yeah, what questions would you ask if you pulled that bolt out on the bottom?
I would ask him, what did the rest of the bolts look like? Let's pull some others out. Let's measure the stretch on the bolts. Were the bolts reused? Or also, how are the bolts torqued at the last repair or the last overhaul? When's the last time that the torquing tool was calibrated or calibration was checked? Things like that nature, probably.
Yeah.
Moving on. So on this slide here, I have a picture of two different rod caps out of engines that have experienced both types of damage. The rod cap on the right is a machine connecting rod parting face, meaning that this face here that we're looking at, it goes against the connecting rod itself. This is the cap that we're looking at. So the bolt's going to come through here and it's going to bolt it to the connecting rod and stay tight and not move. And then the bore is going to hold the connecting rod bearing. With this type of cap, the typical manufacturing process is that they forge the rod and then they do the machine work to the rod, and they do the shot peen work to the rod, and then final machine work or grind. But they cut this cap off of the rod. It's one solid forged piece. And they cut it off and then they do the machine work. If you look closely, you being a machine shop owner, you're familiar with what machine tool marks look like
Exactly.
across the surface. And the machine tool marks, understanding what machine tool marks or what part surfaces should look like after the process has been performed, can help a service technician exponentially in determining what wear types are occurring.
Mm-hmm.
And when we know what wear types are occurring, then we can go after and attack the problems that create that type of wear. So this one here, it's a machine face, but we also see this damage in these areas here, right? So this damage in these areas here is what is known as fretting corrosion. It's not general fretting. General fretting is loose, parts vibrating, oscillating against one another, polishing surfaces. When fretting corrosion occurs, parts are clamped tightly together, typically bolted joints or joints held tightly together with fasteners or threaded fasteners. And that joint gets overloaded, which means that the friction in the joint can no longer keep those parts from moving. So we move with very low amplitude. We're not moving real far, but with very high frequency. So we're doing it a lot. And to overload this type of joint, what we would typically see is a spun bearing. And if we spin the bearing and there's no bearing material left, sometimes we see that the bearing gets all eaten up and ends up in the pan. And this connecting rod is kind of dangling around in that crank journal, kind of like the dinner triangle on the old Western shows, if you will. So now we've overloaded that joint. We're causing this joint to move, and this is a good representation of the fretting corrosion. And what fretting corrosion is, if we bolt that joint together and we cause it to move with it being bolted tightly, we create tremendous frictional heat. That frictional heat can reach temperatures high enough that it can actually micro weld from one surface, from the rod surface to the cap or vice versa. When it does that, it leaves pits behind on one piece and it leaves high spots behind on the other piece. So
Mm-hmm.
sometimes we'll see this, that if the temperatures get high enough to oxidize the metal and it's steel that is fretting, that we'll see almost like a reddish orange powder or dust, which is iron oxide, similar to rust. Okay, so the fretting corrosion happens when we overload the joint. So sometimes the joint gets overloaded because of the operator, right? And us, potentially overloading the equipment for whatever reason, and that can cause the fretting corrosion to happen. Sometimes it's component parts that have run thousands and thousands of hours. I'll give you an example. Let's say a G30 or G3600 water pump, if you will. So one of the water pumps on the front of a G3616 has a gear bolted to the shaft, and they experience fretting when they get tens of thousands of hours on them. They experience the fretting corrosion between the gear that's bolted to the water pump shaft. So we see that metal transfer, and we'll see a little bit more of that on the next slide. But let's take a look at this rod cap that's on the left, and this guy here, it looks quite a bit different than the one on the right, right?
Yeah.
So what we're looking at here is what's known as a fractured rod. So they forge the rod, or sometimes they make them out of powdered metal. They will score the inner bore with a laser, much like scoring and snapping ceramic tile. When you break tile, you
Mm-hmm.
put the engineered stress concentrator, and then you put a shock overload on it, and it fractures brittly, and you get the nice straight line.
Mm-hmm.
Well, they do the same thing with these rods. Is they laser score the inside of the bore, and then they put a mandrel in the center of it, and force a taper down through it, and it shock overloads that, and it breaks right in line with the score mark, similar to the tile. It makes a very highly integrated and strong joint when we bolt those brittle fracture surfaces back together. No extra machine work is required. So they'll still have to machine the bore and size the bore. But when we take a look at this one here, if you notice, what this should look like is a brittle fracture, and kind of sparkly and crystalline looking, like a piece of steel that was very hard that broke suddenly.
Mm-hmm.
But you notice that it's super smooth, and peaks and valleys, but it's super smooth and really polished, isn't it?
Mm-hmm.
So that tells me that that guy's been running loose for a while, right? And it's been experiencing general fretting, the oscillation and vibration between surfaces. So we've got two different connecting rod caps here. The one on the left running loose, general fretting with the polishing. The one on the right running tight, but the joint being overloaded. We can still see the machine marks over a portion of the surface, but then we also see the fretting corrosion and pitting damage from metal transfer on the surface as well. All right, so let's move on to the water pump gear that we were discussing earlier. So the water pump gear surface is the picture on the right. The water pump shaft is the picture on the left. If you can follow my cursor on the water pump shaft, can you see all these darkened areas here, Michael?
Mm-hmm.
So this is where metal transfer has been happening. When I see this type of damage, it tells me that that joint has been tight. It's not been loose. If it was loose, Michael, what do you think it would look like?
Nice and well, if it's fretting corrosion, it kind of starts that metal transfer.
Exactly.
That's where that's
But if it was loose, what do you think we might see?
be nice and shiny.
Exactly. Yeah,
Yeah.
exactly. Good, good. Yeah, it would be polished and shiny. So we got the metal transfer going on, and what's happening is it's transferring from the shaft to the gear surface. So we would take this gear surface and we would flip it over and put it right down on that water pump shaft. Those would be the mating surfaces. And this is a fairly common anomaly that happens on these water pumps, just simply due to uh, the engineering design of the joint, and the vibration characteristics, the load, the speed of operation, and the length of time the part's been in service.
What engine is this off of?
This is off of a G3616 cat engine. So when it creates a problem, Michael, is when this fretting corrosion has happened, we have taken the material from where we see the dark pits in the picture illustrated on the left.
Mm-hmm.
We've taken that material and we've micro welded it and made high spots on the gear surface. So what ends up happening oftentimes, and I've seen it actually occur, is they remove the water pump. They set the water pump on the ground. They buzz the bolts out. They lift the gear up and they move it over to the new water pump, and they set it on. They run the bolts in and torque them without examining those surfaces. When we do that, it would be no different than if you were putting a new tire and wheel on your car, and the back of the wheel had a bunch of dirt on it, and you went ahead and clamped it on and tightened it anyway. Yeah, it's going to run. It's going to look good until it comes loose, right?
Right.
It starts
Until
to
it
break
doesn't.
that stuff up. Exactly. You lose the torque on the fasteners. So with these high spots that we see exhibited here from the fretting corrosion, those start to wear down. We lose torque on the fasteners. Usually what I've seen is a couple of the bolts will break due to bending fatigue fractures or reverse bending fatigue fractures. And then the bolts hold the joint tight. What keeps the joint from moving is the frictional force between the lateral surfaces. So now we've lost some of that clamping force because we had two fasteners fail. So oftentimes the rest of the bolts will shear off because the
Mhm.
bolts aren't typically, unless they are specifically designed and applied as a shear bolt, most fasteners are not designed to experience bending loads or shear loads, just strictly tensile or stretching loads.
Yeah.
So when those bolt heads break off, they get caught up in the front of that gear train of that big expensive engine. And that requires a lot of disassembly time and replacement of very expensive gears and a lot of clean out, depending on how much debris was generated during the failure process.
Yeah.
So that's kind of a general fretting and fretting corrosion 101, if you will. I hope that helps. I think that's all I've got today on fretting and fretting corrosion. We can talk about it a little more if you'd like.
Sure.
Get rid
Yeah,
of
I think that yeah, I think just breaking down bolts and changing things out is a common thing. I don't know how often it is that folks really inspect bolts to look for, like the pictures you had, bolts being like a really telltale sign of what might be going on the other side.
And we see that often, Michael. We do have a fasteners module that we teach as well.
Hmm.
So with most of our modules, we'll cover how that particular component part is manufactured, the steel that's used, the heat treat processes that may be used, so you can familiarize yourself with all that stuff. So if one does fail, the more information you have relative to that, the easier it can be to help you get to the root cause of the problem or to recognize problems or anomalies.
Yeah.
So with our fasteners, I'll just throw a couple of things out there. When you do fastener inspection, always look at the underhead clamping surface and the underhead fillet radius, meaning where the clamping surface comes to the shoulder of the bolt. Make sure there aren't any nicks, dings, corrosion, or any type of physical damage in those areas. Or if they're highly polished, then that fastener should be replaced.
Yeah.
Obviously, we want to check fastener length, check fasteners for stretching, always looking for signs of cracks in them as well. Any physical damage or what we refer to as plastic deformation, the part changes shape, steel changes shape,
Hmm.
those types of things. Corrosion is the enemy for fasteners, especially when it gets in the high stress concentration areas. And I'll give those to you. There's three typical high stress concentration areas on a fastener. That's going to be the underhead fillet radius area where it transitions from the head into the shoulder. It's going to be the first thread root after the shoulder. And the third one is going to be the first engaged thread root, whether it engages into a threaded hole or a nut. That's commonly where we see fasteners break or fail.
What do
There are
you,
other failure modes as well. It's just too much to really get into it, but maybe we can do another podcast another time on fasteners if you like.
oh, I think we probably could because I mean, that's what holds everything together. I mean, you don't get to
Good
bolt
point.
anything up without a fastener. So what do you do if you're in the field and you've got to make some changes, you've got to change something out, and you've got a bolt that just doesn't look quite right? Is there I mean, you got to get this thing back up and running. Is there you can't bead blast it or you can't you don't have glass beads to clean it with? I mean, is there a material or I mean, if the bolt is deformed, just throw it in the trash and go on. But what would you recommend as like your absolute go-to on cleaning bolts in a hurry? Got to get back up and running.
Well, if I'm cleaning bolts, a lot of guys are just going to take something like a can of component cleaner and spray the bolts off, right? And then maybe blow them dry. A wire wheel on a die grinder for threads, just not too aggressively,
Yeah.
because you can push metal around with a wire wheel as well with enough force
Mm.
and time. But those would probably be the two primary things.
There's there's not like a secret sauce that you know about that.
The whiz bang solution. No, I don't have one of those.
Okay.
Um, no, I wish I did. That would be great. Boy, I
Maybe you
could
should come up with a
be a
FAS,
billionaire. Yeah,
the FAS training special boat cleaner.
there we go.
Yeah.
So yeah, we see the remanufacturers when they reuse fasteners, um, they have different cleaning methods. It just depends on the fastener, what the fastener does, what component it holds together. Some of the fuel systems we'll see them go to the point of using something like an ultrasonic cleaner, where a lot of the other fasteners may go in a solvent tank, so they'll get some naphtha or mineral spirits, where others may just go in a basket in an automatic parts washer with a caustic solution or something like that.
Yeah.
But anytime that they come out, they should always be thoroughly inspected. Another good tip for the guys out there doing it, and I'm totally guilty of doing this myself. It's kind of funny. Most of the problems that we run into, I've probably seen or contributed to at one point or another in my career before I knew any better. But taking bolts out that you're going to reuse, especially any critical fastener, and a critical fastener, in my mind, is any fastener that is inside of a component or something that is like torquing a cylinder head on, right? Or holding another component to that component, such as the water pump, the water pump gear, drive gear fasteners, things like that. So it's important that when we handle those critical fasteners, that we handle them carefully. And man, I'm just as guilty as the next guy for buzzing the things out and throwing them in a bucket, or throwing them in a box, right? And when you do that, and sometimes these bolts are big, and then inadvertently other parts get thrown in on top of them, and you can cause some significant physical damage to those fasteners, which can potentially cause a failure. As a matter of fact, I believe it's in the December issue of Gas Compression Magazine. If you go back and you look at that article, you'll see where a bolt was mishandled and it caused an engine failure and caused a connecting rod to go through the side of the block,
Oh,
simply due to mishandling and lack of inspection of the clamping surface of the bolt. The pictures kind of tell the story on that one.
is that a what went wrong
It is, yeah, that's the
episode? Yeah.
column that I'm writing for Gas Compression Magazine now. Have a lot of fun with that. All right, so I think the viewers maybe got some good stuff on fasteners and general fretting and fretting corrosion. Any other questions or anything you'd like to
No,
cover?
not at all. I agree. I think your stuff is short and sweet to the point with the pictures, and it gives everyone a chance to kind of get a visual on what they're looking for when they see what they're dealing with. They kind of can ask the right questions. So just a real quick, you mentioned the modules that that you're teaching. So what if folks are, wanting to get some more in-depth training from FAS, what is what's your schedule looking like? It's late January as we're recording this, but when are your classes coming up next?
So our open enrollment classes, we've got one in July in Colorado Springs, July 29th through the 1st. And I believe we have another one in October in Colorado Springs, which is October 8th through the 11th.
So if folks are interested in open enrollment, where do they go to do that? Which website?
So that would be www.fas-training.com. So FAS, Failure Analysis Services-training.com. And I don't know how I could forget this one, but in May 13th through the 16th, we'll have an open enrollment in Pittsburgh, Pennsylvania, or just outside of Pittsburgh in Canonsburg. That's going to be the week following the Eastern Gas Compression Roundtable.
Great. That's awesome.
Yeah. So we've got those three classes planned right now. The first one's about full, so classes fill up fast. But
Mhm.
what we're getting here in the podcast is just a little snippet of what our classes teach. So I hope folks enjoy it, and we hope to see you maybe in the classroom, or if you run into into problems with components and you have questions or you need an analysis, feel free to reach out to us. You can get in touch with us through the website.
Awesome. Well, Jim, thanks so much for sharing your wisdom, your knowledge, your PowerPoints, your visuals, all that stuff. You're a great detective. It's fun to dive into this stuff with you. So thanks for coming on again.
Thank you, Michael. I enjoy it.